Hello and welcome to today's webinar, Building Data-Centric AI Applications. I'm John Marini and I'll be the host for today's event. Before we get started, I'd like to go over a few items so you know how to participate in the webinar today. We'll be taking questions at the end of the event, so please ask any questions you have for the presenters using the Q&A pane, which you can access at the bottom of your Zoom window. Additionally, we'll be recording today's event and the link to the recording will be sent shortly after the event. And now I'd like to introduce our presenters today. We have Roshni Malani. Roshni is an engineering leader here at Snorkel AI and is building the core programmatic labeling and iterative model development experience. Previously, she managed teams building internal tools for the AI ML organization at Apple as one of the founding engineers on Google Photos. She received her PhD in software engineering from UC San Diego, and she believes that the true potential for machine learning can be unlocked by collaborating on the data. Additionally, we're joined by Priyal Agarwal, a machine learning engineer here at Snorkel AI. She graduated from Columbia University with a master's degree in computer science, specializing in machine learning. She's previously worked as a software engineer at Microsoft Azure and as an intern at Amazon Robotics. She is a vocal supporter of women in tech and served as the director for Women Who Code Delhi. So we're very lucky today to be joined by both Priyal and Roshni. And now I'd like to turn the presentation over to Roshni.
Thank you so much for that kind introduction. Today, we're going to be chatting about building data-centric applications. It's one of these kind of shifting things that's going on, kind of a data-centric approach. We'll explain what that is and how building AI applications can become much more efficient and collaborative and iterative and get you, kind of a really great solution in a very short amount of time. The next slide is introducing us, the presenters. You got a great introduction already, and so I guess the biggest benefit on this slide is you can contact us on LinkedIn and Twitter, so you have our handles right there available for you. So we're going to start by talking about what is data-centric AI. Isn't machine learning has always been about data? So why are we hearing this term kind of float around more recently? Well, we can understand data-centric AI by starting with a comparison to where it has had been kind of from a development perspective earlier, which was kind of a model-centric approach. In this approach, trained data is seen as external to the ML application development process. You just start with it, thanks to someone else's hard work, and then iterate on the model components. And the focus is on the ML model to be able to learn from that labeled training data. So some of the key operations include feature engineering, model architecture design, and training algorithm design. In many settings, this was what's the dominant mode, a model-centric approach. The data came before the core development processes. But now there's this shift from a technology perspective and a community perspective to treat the model as more relatively fixed instead and spend more time on the data. And so the key operations here include labeling, slicing, augmenting, managing, and curating your data. Training data is now the key focus of the iterative development process and is a key differentiating factor. Actually, successful models require iteration on both the training data and the model. It's not an either-or situation, right? And so what we're talking about today is a relatively shift in focus and how that affects the techniques that we use to both develop and deploy AI applications. So the talk today is going to be centered on these three key principles of data-centric AI. AI is centered around training data. And if the data is the center, then the interface needs to be better than manual curation and must become programmatic. With a programmatic approach, we actually unlock the ability to iterate on data quickly and beyond that in a more guided and prioritized fashion. And of course, AI development workflows have to include the people who know about the data, the domain experts. And by collaborating with them, we can actually accelerate data-centric application development. Our talk today will go into the details of each of these three principles with case studies that really help illustrate how to build data-centric applications in an effective and cost-efficient manner. So the first principle, data-centric AI necessitates an efficient programmatic interface. To help us really understand why we need a programmatic interface for data-centric development, let's take a look again at the typical model-centric iteration loop. Here you can clearly see how data scientists and subject matter experts are operating in silos with no common means or tools for collaboration. Labeling data is often seen as a manual, tedious, and expensive process that's done by the subject matter experts. Often it's a one-time task because doing it again would be very onerous. So basically, the data scientists are blocked on the data until it's been labeled and kind of tossed over this imaginary wall. And the data scientists are constrained to iterating on the model with marginal improvement that's observed. So to dive more into the data scientist workflow, we can see a shift from the manual feature engineering to deep learning models. From a practical sense, today's models are much more powerful and push buttons since they learn from these large data sets. But it's less easy to know what to do when something is wrong. And so today we are blocked on data. Real-world cases that need domain or subject matter expertise, maybe from folks who are kind of trained inside large organizations, right? And data is often highly private. Imagine medical records, financial data, right? And data in the real world often has objectives that change rapidly, right? The distribution of data changes or the objectives of the ML application change. And we have to be able to kind of keep up with these rapidly changing goals. And so in all of these cases, manually labeling data and curating it is just a non-starter, even for the largest of orgs. I'm going to dive into a little bit around hand labeling to really illustrate the point. Imagine each dot here represents a data point that's available. For simplicity, you would split into a training and validation set. The validation set would, of course, need to be hand labeled, but also the training set would also need to be labeled. And you try to label as many data points as possible, painstakingly labeling them by hand. As you can see, manual labeling tends to be slow, expensive, and static. Also, there's many ethical and governance challenges around manual labeling. How do we inspect or correct biases? How do we govern the data that's controlled by millions of data points? How do we trace the lineage of how a model came up with a particular label? And so these are some challenges that are kind of critical for machine learning application development at the scale that it's done today. To give you kind of a concrete example, imagine trying to design a clinical trial where we want to understand the inclusion and exclusion criteria. We might have all types of data, such as patient records, billing codes, scans, etc. And we want to be able to label programmatically in order to maintain kind of privacy safe and compliance. And so here, as the objectives change for the trial design, perhaps there's new test results to incorporate or latest medications or current prognosis, right? We want to be able to adapt, and it becomes really difficult when we're labeling each data point kind of manually. And so to tell us more about programmatic labeling, I'm going to hand it over to Priya.
Awesome. Thanks so much, Roshni, for explaining all the pitfalls in the traditional AI application development cycle. So as an alternative to working in silos on the labeling and training aspects, what we're proposing here today is an iterative development loop focused on the data itself. So the process is kickstarted with labeling data using programmatic labeling. We'll discuss the details of this in the coming slides. We'll also talk about what we mean by the second step here, which is integrating data. We use the labeled data set from the first and second steps to train a machine learning model. Traditionally, in the last step of the development, practitioners focus on hyperparameter tuning of models as the only source of improvement, right? That's also because traditionally we have considered data labeling and model training as two processes separated by a wall, as Roshni mentioned before. But here in the analysis stage, we also try to identify gaps in model performance by utilizing a number of analysis tools and by looking at the data points where the model predictions were incorrect. And so as a result, we go back to stage one, refine our sources of supervision that we had previously used to label our data here, and continue on with the cycle, the same cycle. And this loop is kind of not limited to the first time you're building your application. The same iterative loop can be repeated after deployment for, say, monitoring the size of production data or changing your application or labels when you detect some data drift, for instance. So let's talk about programmatic labeling, which is kind of the key enabler to the data-centric iteration loop that we're talking about. So instead of labeling each data point painstakingly by hand, programmatic labeling allows you to label entire sections of data using these abstractions that we call labeling functions. We can think of labeling functions as code for labels, where the input is a data point and output is a label. And you can dump each and every source of signal that you have to help inform labels for your data. But of course, these LFs can be noisy, or they can correlate with each other, they can overlap with each other, and so on and so forth. So this is where the power of weak supervision comes into play. As weak supervision-based frameworks like Snorkel denoise and aggregate all of these sources of supervision to give sanitized labels. And as you can see here, programmatic labeling is a much more efficient way to label your large training sets in a fraction of time, really. So what do I mean by weak supervision? Weak supervision kind of allows you to rapidly encode domain expertise to program your training data sets. Now that's really powerful because with this you can encode and wrap up different sources of supervision. It could be pattern matching. It could be just a database lookup. It could be using existing organizational resources or third-party models or even crowdsourced labels, or most importantly, encoding intuitions from subject matter experts. So all of this can be wrapped up in this weak supervision paradigm to help inform supervision for our labels. So for instance, let's say I have a financial machine learning application wherein I want to classify whether a particular financial document is a credit agreement or not. So a few examples of LFs could be pattern matching based. For instance, if the title of my document has the keyword credit, then I want to label it as credit agreement, for instance. Or if any keyword in my entire document matches a list of some financial terms that I have in my organization existing, then I would call it a credit agreement. Or if I don't really want to reinvent the wheel, I want to be able to use my existing resources. And so if my legacy system thinks that it's a credit agreement, then I call it a credit agreement. So now that we are leveraging all these noisier but more efficient supervision sources, the trade-off that we are making here is speed for noise. So we need a mechanism to denoise and aggregate all of these supervision outputs. Now, this is where weak supervision frameworks like Snorkel come into play. They allow you to dump all your expertise, take that as input, and combine all of that into sanitized labels. And of course, at Snorkel AI, this is relevant to the work that we did and continue to do on the academic side, right? For instance, how do you combine the outputs in a provably consistent way? And so here, what I want to say is that weak supervision ends up being a key foundation technology that lets us iteratively build not just models, but also the training data itself. And additionally, now that we have encoded all these forms of supervision in a programmatic way, it becomes really easy to audit these LFs and change them if needed. The concepts that we're talking about are applicable not just to text, but all other data modalities as well. For instance, for an application which detects if a tumor in an image is, say, regular or not, we could write an LF which encodes a doctor's expertise and intuition. So something like if the tumor has a high perimeter to area ratio, then I want to label it as irregular. Or for time series, you could say if the value of my data point is different from the past 3 data points, for instance, by 50%, then I want to label it as anomaly. So the second key takeaway that we want to highlight is that using these concepts of data-centric AI, you can iteratively develop your application in a guided and prioritized fashion. To really drive home the point about this iterative development that we're talking about, let's take what we call the hello world application in machine learning, which is classifying ham versus spam emails. I took a data set that contains 500,000 plus emails from 150 employees of the Enron Corporation. This data set is actually publicly available on Kaggle. And each data point is an email, which contains a subject and a body, as shown here in this example. And we want to predict whether an email is spam or not. So for my application, my input data is the set of emails that I have. Now, I could write some very basic LFs to get up and running. I have two LFs here for this case study, one each for ham and spam. The ham labeling function says if email body contains discuss or see attached, then I want to label as ham. And similarly, a very simple LF for spam says if email body contains weight loss, then I want to label it as spam. So these are just like one simple LF per class that I have written to just get up and running with my application without using any ground truths till this point. So now using weak supervision frameworks like Snorkel, I get my training data set labeled from this labeling functions, which in turn I use to train a final machine learning model, such as a simple model like logistic regression, to get my final predictions. So one thing that I want to note here is that I don't really need any hand labeled data for getting up and running with my application. But having said that, a small amount of ground truth for evaluation splits would be helpful to anchor the development on, like Roshni mentioned earlier. So with this one iteration, I got an accuracy of 87.3% using a very simple logistic regression and count vectorizer based model. By this iteration, I mean the process of writing labeling functions, getting your training data set, and then training a machine learning model to get final predictions on it. So this score is not bad, but let's see if we can, if and how we can further improve our performance on this task. So one frequently used error analysis tool, one that we're all familiar with, is the confusion matrix. But let's see how we can use this error analysis tool in a data-centric fashion. Here I have ground truth on the left and predicted labels on the top. The biggest error bucket, for instance, that I see here is this one, where my model predicts some emails as spam, but the ground truth for them, sorry, it predicts as ham, but the ground truth for them is spam. So I want to improve my model's performance by handling these false negatives here. So what I would do is kind of, double click into this bucket and actually dive deep into the individual data points which my model is falsely predicting to see if I can find some pattern in that and kind of improve from there. So here I have a few examples that I found. Where the predicted label is ham, but the ground truth is spam, right? So here the subject is subject of the email is help my family out of this, and then there is a huge body in here. Another email says has the subject, I want to help you feel healthier, and then yet another email has the subject with a keyword help and nothing else. So one common pattern that we are noticing in these three data points, for instance, is the presence of this keyword help recurrently. So a common, one first idea that comes to mind is to write another LF to improve supervision in this particular bucket. So this could be as simple as saying, if email subject contains help, then I want to label my data point as spam. So this is my iteration 2, where I wrote a new LF. I again ran the weak supervision framework to get a training set, and then I trained the same logistic regression model on top of it, which yielded a 2.4% increment in accuracy for me. And note that I'm using the same model as before. I am not doing any hyperparameter tuning at this point. So here we can notice that the previous number of data points incorrectly classified in this bucket was 39, which has decreased to 25 now. So this is an improvement here. However, in this confusion matrix, we still see that the biggest error bucket is the same one. So maybe if we can go back and look at the data again, we'd be able to find more patterns. Another error analysis tool that we have at our disposal is the label distribution graph. So the x-axis shows the percentage of data points covered, and the y-axis shows each label, which in our case is spam and hem. Now there are 3 lines for each label, one each for the ground truth. The second one is for the training set, which is kind of the output of the LFs that we write. And the third one is the final machine learning model. Excuse me. As you can see, the ground truth for this distribution for ham and spam is pretty much the same. So my data set that I have originally isn't imbalanced. However, the current training set has more hams here than spams. And similarly, there is an imbalance in the final output predictions for the machine learning model. So this means that our coverage from labeling functions for spams is not enough. So how about we start working on this, on bridging this particular gap? So kind of following the same pattern as before, an idea that comes to mind is to write a new LF that would cover more data points for the spam class. So I went through a similar process of diving deep into the data points that were being misclassified to find a pattern. And another simple LF that I came up with says, if email body contains money more than 2 times, then I would label it as spam. So this is my third iteration, right, where I'm going back to the data, writing new LFs, or like looking at individual data points to find some patterns, writing new LFs, and then getting my training data set and training a model on top of it. Another idea, which we have frequently used in our traditional pipelines, is to fight the class imbalance by oversampling. So the minority class, which in my case would be the spam class. So I would just, I can, of course, use these existing ideas to improve my model, right? So I would just oversample the spam class in my model training to improve performance. So with this third iteration, I got a 2.7% increase in accuracy using the same model as before. So overall, we have seen about 5% increase in accuracy through this like tiny time-taking iterations through the data itself. Note that the label distribution graph that I have now looks pretty balanced. So I would say this is a pretty good performance that I have here. So hopefully this mini case study kind of showcases a little bit of how, by using these very specific error analysis tools that we have, we're able to take the guesswork out of improving our model. So it's much less about training, much less about tuning the hyperparameters or staring at loss curves, which I am guilty of doing, but much more about specifically addressing error buckets and driving insights by looking at these data points individually and making very, very systematic improvements and forth.
Thank you so much, Priyal. There's one question in the chat that I'd love your perspective on. One of the attendees, Christiane, asks, why not just use the rules in your labeling functions instead of a machine learned model on top of them? Wouldn't the machine learned model just be trained on these deterministic rules anyways? And so wouldn't you get better performance using just the rules themselves?
That's a great question. So I would like to think of it as this way. Using these rules, you're encoding domain expertise and kind of injecting what you know about the data and encoding that in the form of labeling functions to get a training data set. However, you kind of need a machine learning model on top of it to generalize over your entire training data set. So let's say if you have a few data points that are just like individual data points that are not being covered by these generic rules, what your machine learning model would do is learn from your entire space that your data lies in and then try to predict on top of that. Does that make sense?
Yeah, I think that makes great sense. I think the way to kind of make sense of this is that the rules give you just patterns in your data, right? And the same pattern, different patterns might apply to a particular data point, right? So which rule should you use and things like that is what kind of the label model helps us denoise and make sense of, and then training a model on top of that will help us, as Priyal said, kind of generalize beyond just the rules to points that we haven't covered yet. Awesome. So we're going to go on to kind of the third principle of data-centric development, which is understanding how this shift to focusing more on the data is leading to more performant AI systems, but also being able to go beyond that to understand, and make systems that are more fair, more robust, and more scalable. And so, by focusing on your data, we have to think about who knows your data best. It's your domain experts. And we will see how by empowering your domain experts with multiple ways of sharing their expertise, not just the label, but the context and nuance of it, will help you actually accelerate your development of AI applications. And so what we need to do is kind of unblock data. We want to start thinking about how we can have the data scientists and machine learning engineers in an organization work together with the subject matter experts to capture knowledge most efficiently. How can we collaborate to maximize the value and the velocity of the data labeling process? We can get higher value annotations by allowing subject matter experts to use their time more efficiently than just tediously hand labeling. We want to maximize the transfer of their knowledge. And with higher value labels and more context information about the data, we actually end up getting more accurate labels. We also work with them to increase the velocity of getting these more accurate labels. We must have less friction than kind of emailing spreadsheets back and forth. So the key insight here is that as we shift from focusing our iteration process on the model to iterating on the data, we need to bring the power of modern collaboration tooling. Think Google Docs, think Git. All of these real-time collaboration features with version controlling for our training set. And so the goal is to kind of help you reduce the development time and improve the quality in terms of correctness and performance. So to unblock your data, we're going to actually build multiple ways to capture domain expertise from within the same product. I'm going to give you a high-level overview now, and we'll explore each of these features in depth with a case study. So some examples of higher value inputs. These are ways to kind of maximize the bandwidth of information we can get from our subject matter experts, as to provide them with the ability to give their expertise at many levels, starting with comments, which are just kind of free-form context about a data point that might be providing the why behind a label, tags, which will help kind of catch kind of properties about your data points, allowing us to kind of cluster the data in ways that might provide deeper insight. Of course, the labels, kind of serving as ground truth. We also want to give them kind of low-code, easy templates that help kind of capture patterns in the data to start helping them to label their data programmatically, and of course, give the kind of full code ability to encode all of the heuristics and domain knowledge as well. This diversity of inputs allows subject matter experts to share rich information about their data with the data scientists, kind of multiplying the value that they can provide. And also, we must kind of lower the friction so we can kind of increase the iteration speed by working together in an integrated kind of product. And here we're going to, make sure that everyone, both domain experts and data scientists, see a consistent view of their data points in full context, kind of no more passing snapshots of spreadsheets back and forth. We should be able to kind of request annotations simply with a shared link, get real-time updates of the labeling progress with full support for versioning. And when there are difficult splits, we have to be able to kind of take portions of the data that the data scientists have a hard time labeled programmatically or covering with model generalization, and kind of focus the manual labeling efforts of the subject matter experts with the push of a button. And so to show you, not tell you, how this approach kind of enables AI teams to collaborate both synchronously and asynchronously to get labels with more value at higher velocity, let's dive deep into a case study. Let's imagine we operate a bank called Snark Bank. This is a fictional bank that provides loans to small and medium-sized businesses. This is a running fictitious example. that I'm going to be using today, kind of based on lessons that we've learned by working with real use cases. It's going to demonstrate the quality and speed with which you can adapt to changing business requirements, such as your label understanding evolving, your label schema changing, or your data drifting. At Snark Bank, let's say we have highly skilled loan officers that help us evaluate business loans. These loan officers kind of specialize in specific industries, of which there are thousands. As you can imagine, the loan application for a boutique cupcake store is going to be quite different from one for an automobile manufacturer. And so the goal here is to build an AI application to route a new loan application to the appropriate loan officer who specializes in that industry. So to start us off on this classification application, we're going to have 500,000 loan applications in our database. We have 1,000 classes and 0 labeled data points. Our data scientists and subject matter experts have sat down together to capture expertise as heuristics, using some of the same kind of technologies as Priyal showed you earlier. And the first idea that we could have is if the exact text of the label or the industry is in the loan application, then that's the label. We could use some keywords from a dictionary or generic ontology to also help us programmatically label, or we could also add some of the auto-suggested labeling functions that our platform provides for you. And so during this process, we've generated about 300,000 data points kind of programmatically labeled and ready for training. So how do we evaluate whether any of these heuristics are any good? Well, luckily, we all already started this process of collecting some hand-labeled ground truth for evaluation. We only selected a tiny random subsample, about 1% of our data points for validation, because that's all we really need. Because we want the highest quality labels we can get for our test set, we asked several loan officers to label the same batch of data points. And they don't need to finish annotating all the data points. We can just give them kind of a fixed amount of time and then take a look at what they've done, see their kind of agreement rates, aggregate the data, and commit to ground truth and be ready to use for evaluating our model. Instead of pinging for progress and being unable to see partial results, we're actually going to build this into a full kind of tool here. And we're going to kind of basically have the senior loan officer make sure that the junior officers who are labeling independently within the same product are on the right track. And so you can see the overall completion rate, the daily annotation rate, and the individual annotator completion status. And to make sure that the quality of labels is high, we can also measure inner annotator agreements, optionally broken down per class. Furthermore, we can denote the senior loan officer, Annie in this example, as an expert and see her agreement rate with the junior officers. We can choose which annotators to aggregate before committing the labels to ground truth. Now that you've seen the basics of creating batches for annotations, which can be analyzed, aggregated, and committed to as ground truth, we're going to walk through 3 scenarios that demonstrate the dynamic, messy environment in which long-lived AI applications tend to be developed, where the iterative loop of improving model performance requires data scientists to collaborate with their subject matter experts in the same product. As you will see repeatedly, collaborating on the data will increase the value of our data and the velocity. All right, so we're going to take a look at the first example, which is when the label understanding changes. So imagine our data scientists have trained a model, are looking at the analysis and kind of digging into the analysis for each class. And they recognize that the annotation instructions weren't clear and they were interpreted differently. So for example, the keyword nursery was understood as garden supply, or some others interpreted as childcare. And so we want to filter the data points about nursery and click to create a batch for annotation, right? These are our known unknowns that we're looking at. And our data scientists and subject matter experts are going to refine our labeling functions or create new ones, retrain our model, rinse and repeat. And so hand labeling a few data points helped us to kind of provide more confidence on our model evaluation. And so this example really illustrates the velocity. If filtering to create a batch wasn't as easy or as integrated into our product, then we possibly wouldn't be able to address kind of the messy ground truth labels to ensure our model performance metrics are as accurate as possible. Another common problem is that the label schema tends to change. For example, you may want to add or remove a label, split a label, merge labels into one. So the example here is to split the label restaurant into two different ones as kind of culture is changing from brick and mortar to also including kind of food trucks. Mostly because kind of the loan application amount will be quite different and they're going to go to kind of two different loan officers. So again, we're going to kind of rinse and repeat the process of getting subject matter expertise kind of input, refine or add labeling functions, and request kind of targeted hand labeled data for ground truth for our evaluation. We can also request annotators to add tags for property of the data that we care about. That might kind of inform our labeling functions, such as price or popular meal times. And so you can see that you can actually get more value, a little bit more information about each business to inform how we kind of create or modify our labeling functions. And as a last example, let's take a look at data drift. In this situation, we kind of have deployed our model and identified a particular slice of production data that we want to monitor. Let's say pharmaceutical companies. And we tend to notice this drift in label distribution for a particular class. Turns out that lately, there have been more loans coming from businesses involved in vaccine manufacturing industry, as well as industries involved with the associated kind of transportation infrastructure. Not only are we able to identify this trend quickly from within the product, but we're also able to address it. And so as a result of kind of being embedded in the same product as data scientists and having been through the collaborative iterative loop many times, our domain experts are now able to identify patterns and encode them using kind of these low code interfaces. And so this example actually demonstrates both the value and the velocity of our data labeling kind of increases over time as you iterate on your AI applications collaboratively. So let's review the key takeaways from today's workshop. First is that data-centric AI application development requires a much more efficient interface for our, labeling our training data. That is specifically, it requires programmatic approaches. Using this programmatic approach, we can actually unlock this iterative development loop focused on our data that's actually guided and prioritized, as Priyal demonstrated earlier. And finally, by collaborating with the folks who know our data best, our domain experts, we can actually accelerate data-centric application development. There's a lot more resources at the website below. Thank you all so very much for attending. Thank you to the entire team at Snorkel who kind of helped us put this together. Thank you to my co-host Priyal. Thank you all for attending. We're happy to help answer any questions that you may have.
Thanks, Roshni and Priyal. We're really looking forward to taking questions from everyone. So as a reminder to everyone on the audience, you can still submit your questions using the Q&A pane or the chat here in Zoom. And we have one question from Amin, and apologies if I've not pronounced your name correctly. I'm going to direct this one to Priyal and Roshni. The question is, can we say that the labeling functions play the role of weak voters? Is there some measure of similarity that allows giving weights to these labeling functions?
That's a great question. And I would say yes, we can think of labeling functions as being weak voters in the weak supervision paradigm. And the weak supervision frameworks like Snorkel have the job of actually giving weights to each and every source of supervision that you input in the form of labeling functions. So it'll kind of try to analyze how the different LFs are voting on each data point, how much they are correlating, how much they are conflicting, and so on and so forth. And it'll try to kind of measure similarity in some sense and give weights to each of these labeling functions while labeling every data point. So just leave all of that to Snorkel.
Great. And one kind of common question we get, maybe Priyal and Roshni, I think it's related, how could I use my existing manually labeled data in Snorkel Flow in conjunction with labeling functions? Can you expand on that a little bit?
Yeah, sure. That's a great question. We typically use the manually labeled data and keep it separate for the evaluation splits. So the validation and the test splits that are typically manually labeled. But in the grand scheme of things, those splits are kind of a tiny fraction of the entire data set that we typically have. So the train split, these days, like all organizations have huge amounts of data. So we can incorporate a huge portion of that as the training split, which can be labeled programmatically through Snorkel. And then we validate the performance of our models on the validation and test splits, which are typically hand labeled. In addition to that, when we are writing these labeling functions, we can also sample just a tiny portion of that manually labeled data into our training split, and we can validate the performance of our labeling functions onto that manually labeled slice of training data. So for example, if you write an LF which says, if my document contains credit in the title, then you would be able to validate the hypothesis of this labeling function on that manually labeled data. So you would see some metrics like precision and coverage. So the percentage of data points which are actually labeled as credit agreements and have credit in their title is, say, 90%. So maybe 10% of those manually labeled data disagree with this hypothesis that we have in this LF. So we can, overall, we can use a tiny fraction of manually labeled data to help writing the programmatic interfaces. And then we can also use this manually labeled data to validate the models.
Great, thank you. And another common question that we get is related to subject matter experts. And the question is, how much engineering effort is needed to set up Snorkel so that SMEs can easily see the data and help with iterative error analysis?
Yeah, that's a great question. Sorry, before I answer that, I still have one more thought going on about the previous question that I wanted to share. It's great if you have ground truth. You can bring it into Snorkel and help you develop it. But I wanted to make sure it's clear that you don't need any ground truth to use the Snorkel Flow platform. We've worked with some customers who it's really hard to manually label any ground truth. So for example, if you have network packets, it's really hard to kind of understand what's in that network packet and be able to manually label it. But you can describe patterns that you're seeing and encode those as labeling functions. And so kind of going back to maybe a question somewhere else in the chat about being able to kind of validate or see how the labeling functions kind of work together. We assume you write these labeling functions with the best of intent, right? That you're trying really hard to find patterns that are representative of things you're seeing in your data. And so I kind of look at when labeling functions conflict with each other or don't, and help weigh the labeling functions in that way. And then we'll give you a model, but we won't be able to, we can generate a model, but again, as Priyal said, you might want a little tiny bit fraction of hand labeled data just to validate or see how your model is actually performing. So I just wanted to clarify on that point. You asked a great question, John, about the amount of engineering effort to set up Snorkel Flow. One of the things that's really special about Snorkel Flow that really excites me is because you don't need as much hand labeling, you don't need to necessarily crowdsource your labeling efforts. You can actually keep all your data in-house and keep it private on behalf of your users. And so with that said, we provide Snorkel Flow both as a hosted service, and we allow you to deploy it on-prem. And so deploying on-prem is going to take a little bit of installation effort for sure, but the trade-off and the benefit you get from that effort is you get to keep your data private and in-house. And so, we offer very simple kind of installation instructions. We can actually deploy air-gapped if privacy is that much of a concern. And so we can help you, kind of walk through all of the steps to install it, test that it's working well in an air-gapped situation. We've built a bunch of connectors with data warehouses that you can kind of easily import your data and get going. And then after that, we've got a bunch of tutorials to help you get started. And the idea here is you don't have to wait for your data to be labeled. You can work with the subject matter experts in-house and just start writing labeling functions. And it doesn't matter where you are in the ML application development process. You can use anything that you have built up to date or build it all in Snarkle Flow. And so that's kind of the magic. And so in general, I think it would be pretty low an engineering effort, especially if you went with the hosted solution if privacy wasn't a concern.
Thanks, Roshni. I'm not seeing any other questions, so just in case anyone else has a question, feel free to submit it either in the chat or the Q&A panel. And if not, we're probably going to end the webinar here just a few minutes before the top of the hour. Great. Well, I'm not seeing any questions. So again, thank you, Roshni and Priyal. And I do want to make a call out for everyone. If you do have the opportunity, please take a few minutes and go to snorkel.ai/join the community. And if you join the community, you'll be able to stay up to date on the latest news and events from Snorkel. Plus, all new community members receive these really cool Dr. Bubbles socks. So those are always really fun. And again, thank you everyone for taking the time to join us today. And we look forward to seeing you at a future event with us. And have a great rest of your day. Thank you, everyone.
Thanks, John. Thanks, everyone.
Thank you.